Let me know if the screen is visible.
Yes, sir.
Yes.
Yeah, right. So far, what are the things we have covered? I mean, loosely speaking, for this particular class, you need to understand how an NPN transistor works. I mean, at least for switching, and how a 555 can be used to drive a motor. So these two things, if you recall, and or if you understand properly, today's what happened? Someone wanted to ask something, or so if you understand these two things, then it should be fine. Today's class should be not much of a hurdle to learn. So in today's class, in addition to NPN transistor, we must also look at PNP transistor switching. So, and the culmination of these will be in the form of what is known as an edge bridge driver for DC motors. Okay, so just give me a few minutes to set up my space. There's a lot of things here, and I'll be right with you. One moment. Yeah, okay. So let's continue here. At the moment, I don't have the circuit with me right now. So let me just draw this schematic and then we'll proceed. So an NPN transistor. Okay, it was something like this, and you have a collector, base, and emitter line, and what happens is if you have a power supply over here, a voltage supply, and some load and a power supply, and then this goes to ground. If the base is not connected, then there is no flow of current to the circuit, and the moment you have some base current through the circuit, then the circuit gets complete. So the collector emitter line becomes conducting. There is a small voltage drop across the collector emitter line. So this is for an NPN transistor, whereas for a PNP transistor, it is something like this. So you have a base, you have an emitter, and you have a collector. But over here, when the base is not connected, okay, when or rather the base is when the base is held to high, meaning when the base is given a voltage like this, I'll call this VDD. So when the base is given a bias, then this line remains off. Okay, so when the base current exists, then EC line is off, and when the base is pulled to ground, pulled down to ground, then the EC line becomes on. Okay, that is the basic difference. So when you have a resistor going to ground, when VDD is not applied but rather the base is held to ground, then the emitter collector line becomes on, otherwise it stays off. Is the basic difference between the two clear? Here VDD apply, CE on, VDD nothing, CE off. So over here VDD apply, EC on, sorry, off, and VDD. So instead of VDD, when you have base to ground, then you have EC on. Alright, so this is the basic thing that we'll be working with. I will send you some supplementary videos on this, and let us now proceed.
Excuse me, sir.
Yeah.
So in the PNP transistor, sir, you are specifically saying like base should be connected to ground, then only AC will be.
Yes, yes. It has to be
Sir,
specifically connected to ground.
so if it is not connected to ground and not
So it will behave as being no connect and it will stay off, but in circuits you should not let this affect your performance, so you have to sort of tie it down to ground. You should not leave it floating, otherwise it becomes floating by some other means if it gets some voltage stray or whatever. So you should always tie it down to ground.
okay.
Okay, you should not leave these connections dangling in any circuit and not just this circuit.
So,
Okay,
so we are applying VDD as well as connecting it to ground. Is that what
no,
we are
no, no,
doing?
no. So what we can do is to switch this. You can do the following. I can do it with the help of a mechanical switch. So let's say this and this, and I have SPDT switch, single pole double throw switch, meaning this common terminal can either, no, it won't be like this. One moment. So this is the common, and there will be one which is normally closed. I mean, in SPDT mechanical switches, it doesn't matter. So you can have the toggle like this. And what kind of switch are we talking about here? Let me just show you some images. A switch which looks something like this. Oops. This is always a big challenge. Okay. So it's a switch which looks something like this. Alright. So over here, this is the common part, and if the toggle is in this direction, this and this are connected. If the toggle is in this direction, then this and this are connected. Similar to this, so there is always one common terminal. Depending on the switch position, on the knob position, it can either connect this or connect this with the common. Okay, so similar to this is that particular thing that I have drawn. So if the switch is like this, then right now the base is connected to VDD, and this EC circuit, it stays off. Okay, now when I flick the switch, when I flick the switch, now the base is connected to ground, and so EC will become conducting. Is that clear?
So, but if we are connecting to ground, then why do we have the resistor out there? Like
It's current
normally,
limiting. It's current limiting. So IE and IB have a ratio. It cannot be very high. Okay. The same thing. It's the same thing as why you have this resistor as well. It's not just like shorting it to ground. You have to have a current limiting resistor. The current is not going to be very large, so as such this point is tied down to ground. We say that the base is tied down to ground. Okay.
Okay, sir.
You will learn this in electronics. Maybe you are almost there to, I mean, almost at the point where you're going to learn NPN and PNP. Have you been taught this in class yet?
Sir, it is different for different sections. Our section
Ah,
didn't reach till there.
so right now you're in diodes or
Sir, our
Yes, sir,
sir,
diodes.
okay.
sir, our sir told us the base current is important in the PNP junctions.
Hmm.
Then how it is getting off in when the base current does not exist?
That is how PNPs are made. I'll show you. I mean,
Means the electrons in the N junction want to go to the emitter junction, no, sir.
when you
It,
have such a configuration, the flow of current is like this, mostly like this, and some part of it goes to ground through base. Okay. Over here, when it is like this, so IC is equal to IB plus IE here, but in NPN, IE will be equal to IB plus IC. So this is how it works. If you do not allow any IB, then there it will not become conducting. I mean, you will study this whenever you go there. You'll study this. You will see. And we are not driving the transistor as an amplifier. So I leave it to the electronics people to discuss the theory in detail. So for now, with this information, let us proceed. Okay, don't worry about the inner workings. You will be taught this in electronics. So with this NPN and PNP, let us proceed to how we can, oh, come on, how we can make an edge bridge. Okay, so let me draw a very elementary circuit as follows. So let us first draw the motor. So the motor is represented by this. This is a DC motor. Okay, so it has, I mean, these two blocks are to show the commutator brushes. In a DC motor, you have what is known as a commutator and a brush arrangement. You know how a DC motor works?
Yes, sir.
So you have
Yes.
this carbon brushes and you have a commutator ring through which the coils are energized. Now, typically, how would you run this DC motor? You would simply connect this to 12 volt and you can simply connect this to ground and it will start working, right? It's very simple. This is how you can easily connect a DC motor, isn't it? Yes.
Yes, sir.
So if that is not, I mean, that should be clear to everyone. I don't know what I was trying to say. So if you want to reverse the direction of the motor, you simply put 12 volts here and put this to ground. This is simply how you can reverse the direction of a DC motor, right? So instead of this, we want a better way of achieving reversing of the direction without having to remove everything completely. Okay, so what we are looking at is fixed wiring and simple toggling of direction. So let me draw the circuit first and then we can discuss it. Let's try to follow along. Okay, so let us look at this configuration. I've not drawn the entire circuit because this already will help us to figure out. So the red ones, what are the red ones? What are the NPN or PNP?
PNP transistor.
PNP.
PNP.
So
PNP
very good. So they are PNP transistors. Whereas the blue ones are
NPN.
NPN. Okay, perfect. So now let us look at this sequence. You connect this to ground. Let me call this 1, 2, 3, 4. It's easier to understand. So 1, 2, 3, and 4. Okay. So let's do this. So 1, 2, 3, 4. Transistor number and base condition. So let's say that 1 is ground, 2 is VCC, 3 is VCC, and 4 is ground. Then what happens? So because 1 is PNP, 2 is NPN, 3 is PNP, 4 is NPN. Okay, so when 1 is ground, then this collector emitter line is conducting. For 2, when 2 is connected to voltage, then what happens?
It's conducting.
It will conduct. So
It's
collector
also
emitter.
conducting. What about 3?
It won't.
It doesn't conduct.
Non-conduct. And 4?
No, sir.
Non-conduct.
No, non-conduct.
So right now, what is the conducting path to ground? In this case, so this is like case 1. What is the conducting path from 12 volts to ground? It will follow something like this. Will go like this, conducting to ground, isn't it?
Yes, sir.
Yes, sir.
So then the other part of the motor has no connection and the motor will not rotate. So in this case, the motor, no rotation. Okay, so let's get rid of this. So this is no rotation. Let me grab this. In fact, let me get rid of these because you know how this looks. Second case. So 1 is still grounded, meaning collector emitter will be conducting. 2 is also grounded now, meaning it will be non-conducting. 3 is given a voltage, meaning, so now what will happen? 3 will
Not
be on or off?
conducting.
Non-conducting.
It will become non-conducting, and 4 is also given a voltage, so it is becoming conducting.
Conducting.
So now let's see how the current will flow from 12 volt to ground. So from 12 volt, 1 is conducting, then 2 is it conducting? Not conducting. So this is the path it has to take, and 4 is conducting, so it can go to ground. So what does it mean? Over
Rotation is
here,
possible.
rotation is possible. So case 2, rotation possible. And so current is going from left to right, right? Current is going from
Yes,
left
sir.
to right. And this is important because if you want to reverse the direction of the motor, then we would like current to go from right to left. All right. Now let us take a look at the third case. Let us take a look at the third case. So third case, 1 is voltage, 2 is voltage, 3 is ground, 4 is ground. So now, because 1 has been given a base voltage, what does it mean?
Non-conducting.
Non-conducting.
Conducting.
2 is given a voltage, and that means it is
Conducting.
conducting. 3 is given ground, meaning it's a
Conducting.
PNP, it's a conducting. And 4 is given ground,
Non
non-conducting.
Non-conducting.
So for case 3, let us look at the path taken. So who will tell the path taken? Not the usual people. I want someone else to answer. Someone unusual.
So through the
See,
three.
One volt to 3, then the motor, and then 2 to ground.
So like this you mean?
yes.
Yes, sir.
So I
Yes, sir.
commend you people for yourself believing that you're unusual. So that's a small thing. So anyway, you are correct. So now the current goes from which direction? Right to left, right?
Yes, sir.
All right. So now similar to case 1, there will be case 4. So case 1, what was it? Case 1 was something like this, where this became the path. And there can be a mirror situation also. So just swap 1 and 3 and 2 and 4. There can be a situation where this is the conducting path. Nothing goes to the motor. Okay? Do you agree?
Yes, sir.
Hello? Okay, so I'm not mentioning it explicitly. Case 4, you can figure it out. So in both cases 1 and 4, the motor gets no current, the conducting paths are direct. So there will be a lot of current going between this line and this line. But none of the current will be going into the motor because there is no path for it to connect. And because of this, cases 1 and 4, they will cause catastrophic failures of transistors. Because in going to ground, there is practically no resistance. Whatever voltage drop will happen will be between the CE of the PNP and the CE of the NPN. But there is nothing else to restrict the current. The current will be simply VCC minus V drops by R, and R is practically zero. So there will be a huge amount of current going in, and when there is a huge amount of current going in, there will be a huge amount of power dissipated by the transistors, and the transistors will go kaput. They will fail. So 1 and 4 should never happen. Okay, 1 and 4 should never happen. Okay, in fact, all the lines conducting should also never happen. What is this? What is the situation when all the lines are conducting? All the junctions are conducting.
So 1 and 3 are grounded.
So 1, 3 are ground, and
2 and 4 should be VCC.
2 and 4 are
should be VCC.
voltage.
So when this happens, then also you will have catastrophic failure, and you should at no point of time during the operation go into these 3 cases. So the cases of interest are only this and this. During the entire operation, this should be the only 2 modes in which the edge bridge should work. So now let us draw the remaining circuit so that we can have cases 2 and 3. Alright, so let me quickly wrap up the remaining circuit.
So like, is it not possible to have any situation where the motor is in turned off position?
So when you apply, I mean, let's go there. I mean, we'll see it. Don't worry. So this is going to ground. In this circuit, you will not have that. but you can literally have a switch here to turn it off. Okay, SPST. Or there are, I
Sir,
mean, there are many ways. Let me finish the circuit.
yes, sir.
Okay. Okay, so I'm done with my circuit. What is your question?
So we can use two different resistances in the left path and right path, and we can use all the junctions conducting. Then the motor will rotate based on the
No, no,
resistant
no, no,
values.
no. That is not a efficient way of going about it. The one I have drawn is the best way of going about it. So let us see what is there. I have shorted the two bases of the NPN and PNP on the left side. They are shorted. And I have shorted the two PNP and NPN on the other side. Why have I shorted? Because if you look at the logic going over here, 1 and 2 should be having the same condition for either of them conducting. 1 and 2 must have the same condition for either of them conducting. Okay, here this is conducting, here this is conducting. The other is non-conducting. Whereas 3 and 4 must also be at the same condition for either of them conducting. This is conducting and this is conducting. So now let us follow the circuit. When the switch is put at this position, okay, SPDT switch, it's again one of those kind of switches. When it is put at this position, what do you get? So 12 volts, this entire line is at 12 volt, this is at 12 volt, this is at 12 volt, and there is some amount of current that is going to ground. But what is the amount of current going to ground, guys?
So it's 12 upon 100.
So it will be 12 upon 100 kilo
100.
ohm.
120 microns.
So it will be a very small current. So over here you have 12 volts, over here you have 12 volts. So which of this, okay, so this line is energized. This line, what is the voltage at points 3 and 4? What is the voltage at point 3 and 4?
So ground.
It is
Zero.
held to, it is 0. It is held to ground
Ground.
specifically because we have used this resistor which has a very special name. What is the name of this resistor? We have studied this. What is the name of this resistor?
Current.
Huh?
Current limit.
It's not a current limiting resistor.
It's a pull down resistor.
Current.
It is a pull down resistor. Very good answer. This is the pull down resistor. Why? Because it's pulling all the bases to ground when there is no connection. Under normal conditions, this resistor is responsible for pulling this points and this points to ground. Okay. Now, points 3 and 4 at ground, meaning we are now looking at case which? 3. We are now looking at case 3, right?
Yes, sir.
The others, give me a
Yes,
yes. I mean,
Yes, sir.
give me something.
Yes, sir. Yes.
So we have 2 which is conducting and 3 which is conducting. What? We have 2 which is conducting and 3 which is conducting. So 12 volts, it goes to 3, then it goes to 2 and like this. Alright. Now when we flick the switch, when the switch is flicked, what happens? Points
3,
1
4
and 2
become.
are pulled down to ground, right? Points 1 and 2 are pulled down to ground, and 3 and 4 are held at 12 volts. So 1 and 4 are the conducting paths. So we get 12 volts going to this, then, oh, wrong path. 12 volts going to this, going to this, going to this and this. So just by the flick of a switch, one is able to reverse the direction without having to change the entire wiring. And this is convenient because when you want to switch the direction of the motor, you do not want to remove the connections at all times. That is just dumb. I mean, of course, if you just want to test something out, you can do it. But once it goes into a complex apparatus, you really don't want to do this time and again. And in a very complex circuit, this particular act of switching can be achieved how? This little act of switching that we're doing, how can it be achieved electronically?
Transistor.
So using a relay.
You can use a transistor paired to a relay. Both of your, I mean, if you mix both of your answers, it is correct. How? If we mix both of their answers, how is it correct?
Sir, but we cannot use a relay in an integrated circuit, so we can have to use a transistor only.
I mean, you can use multiple transistors, or see, even in a small PCB, you can use a relay. No problem. It's not such a damning thing. Okay, what happened? It's the same relay circuit where there is one normally open, one normally closed. Okay, this is suppose normally open, and this is normally open, this is normally closed. So you can just imagine the entire circuit. I'm not going to draw it again. Okay, I mean, this could be a possible question in the exam, so who knows. I'm not gonna discuss that. Take a hint. Okay, that's not gonna work. Anyway, let that green be there, no problem. Okay, now what have we done? What have we achieved so far? Motor, direction, reversing. Check. Next thing we would like is motor speed control. Any guesses how we can achieve this, the second part?
Sir, by controlling the voltage that we are giving to the motor.
So you can achieve it by controlling this voltage that you are giving to the motor. That's what you said, right?
Yes, sir.
So how can we achieve that? How can we control that?
Sir, PWM.
Very good, very good. So you can achieve it with the help of PWM. So I will write over here simply V in and V in control. So you have a black box. VCC goes in, there is a ground, and V in, that is this particular label, it should appear at the outlet of the black box. So this V in will be percentage duty cycle multiplied by VCC. Pardon me. Yeah. So V in will be percentage duty cycle multiplied by VCC, and we have all seen how this percentage VCC can how this percentage duty cycle will be can be controlled. So how do you control this? I mean,
Sir,
So
using
that's great.
using this
555 timer
555.
and changing.
Very good. So 555 in which mode? In which mode?
Sir, A stable mode.
A stable.
A stable mode. Perfect. So you guys, if you just combine these two, you have successfully made a very important commercially available unit which people sell for a lot of money. Okay, so now you should ask, there should be one question, I mean, in everyone's mind. First of all, how are these resistors chosen? Everyone knows how these resistors are chosen. It's according to the base current, and the resistors, simply you have to look at the data sheet to figure out what is the maximum base current that can go in the NPN or that can flow out of the PNP transistor. Okay, so that will control all the base resistors. So you should be in a position to, so choice of R look at data sheet, figure out IB to saturation, select slightly higher IB. Okay, select a slightly higher IB, look at what CE losses are, and then you know how to do the rest. Okay, this is how you would select the resistors. Okay, the question now is what is the maximum current that you can allow through the motor? What is the maximum current through the motor? It's also a simple answer. It's the
So,
maximal, it's the ICE max for the NPN and the PNP transistors. Okay, maximum current that it will go will be the minimum of the two currents that these transistors can allow. Okay, suppose the PNP allows a maximum of 5 amperes, but the NPM allows a maximum of 3 amperes. So the maximum current that can be passed through this line, of course, this impedance we are ignoring at the moment. But suppose this motor is rated for 6 amperes, and you know that the PNP is rated for 5 ampere and the NPN is rated for 3 ampere. So what will be the maximum current that will go through the circuit?
3 amperes.
yeah,
It will be 3 amperes, otherwise it will be damaged. Okay. So typically you have to make a choice of the transistors appropriately, and in the circuit that I'm going to demonstrate in a while, I have made use of TIP 122 and TIP 127. So TIP 127 is an NPN PNP transistor, and TIP 122 is an NPN transistor, and these transistors are what are known as Darlington transistors. And Darlington transistors allow for higher collector emitter currents, as opposed to something like a BC547 and a BC557. You can make one circuit at your home as well if you were to be so inclined. This is the PNP NPN pair if you want to make it using something cheap. So you can do motor switching for small motors easily using BC547 and 557. You can do high ampere switching using Darlington transistors, but people don't use them anymore because people have stopped using BJTs for edge bridges and they directly use MOSFETs. So something like a IRF P440, IRFN. Actually, in that, then it depends on whether it's a depletion mode, enhancement mode. So, I mean, in this course, I wanted to avoid that complication. When you will study it in electronics, you would be in a position to make these circuits on your own very easily without even referring to these notes anymore. Once, if this logic is clear to you, you stand in a very good position to design such things. Okay? Alrighty then. So, let us go to the practical thing. So just give me a second to set up my table. Let me save this first. Let me save this. So this will be, H. And let me unshare this screen. Let me start my video. Is it video is visible? Yes. Let me spotlight my video. So let me know if my video is in spotlight or not.
yes, sir, it's in spotlight.
Yes, sir.
So let me just adjust. Okay, so is the circuit visible? No. Now? No. Now it should be visible, this part. Yeah. Okay. This is the circuit. I know it, you cannot see any component, but are you at least able to hear me?
Yes, sir,
Yes.
we can.
Yes, sir.
So let me move this stepper motor out of the way. That comes later. So yeah, I mean, what we have over here is the same. We have our DC voltage source, the same one I've been using. We have the circuit and it's connected to a geared motor. Okay, this is a geared motor. So let me just pick this up and show you. Okay, so over here, because I did not have a SPDT at hand, I have used two switches. And the two switches I mean, because I didn't have one at hand, I'm never gonna press both of them at the same time. Because the moment I do, these transistors will blow. They will go into thermal overload and they will be damaged. I mean, there will be magic smoke. So we don't want that. Okay, and the second thing is the base resistors that are connected. So let us make a quick measurement of those. Let us make a quick measurement of those. 4 kilo ohm. Oh, you cannot. I mean, anyway, it's 4 kilo ohm. 4 kilo ohm. 4 kilo ohm. So it's our 4 kilo ohm. So all the base resistors are 4 kilo ohm. And yeah, this is the entire circuit. It's the same thing that we have drawn in the schematic. There's nothing different. So now let me switch on the power supply and let me show you the operation. So the voltage is now 11 volts. I've kept it 11 volts. Are you able to see it? This small,
Yes.
Yes, sir, that is clear.
11.1.
just barely, yeah, okay, 11. So now let me do this. So I press this. Can you see?
Yes.
Yes, sir.
Clockwise. So now release. Now counterclockwise. Okay. No connection changes, just a switch. I mean, just a pair of switches. So these are just like bell switches. You push them and it comes out. But you could use a SPDT like the ones I showed. I mean, the tuck tuck. You know, like three-legged switches. Okay, there are some mosquitoes. Okay. Now I know what you're thinking. I know what you're thinking. You're thinking that I'm thinking that you want me to press both the buttons at the same time, right? Is that what you're thinking?
No, sir.
Press it, sir.
No, I'm
Actually,
not
yes,
gonna.
sir.
I'm not gonna do it because I know what will happen because I have done it in the past. then I'm not gonna. They will immediately give out smoke, and my power supply may get damaged as well. I don't want to ruin my power supply. I don't have. I mean, there is a ampere limiting functionality, but I don't want to test its limit as well. So yeah, that's so. The next part would have been that the power going to the. So I have tapped the power. So let me share screen from here and just tell you what I'm talking about.
So what kind of motor is this?
It's a DC motor, geared DC motor. So the geared DC motor, I don't have one lying around, and I've put this in thermocol. So I mean, apart from the motor being there, it's coupled to a gearbox. So the RPM of the motor is actually quite high, but there is a reduction gearbox so that you can have a larger output torque. And it is used for many applications where you're just looking for torque, not a high speed. So over here, why do you see only one power supply? Ideally you should have two power supplies, one over here and one over here. So I've simply tied them down. Okay, I've simply tied them down and nothing else. Is that clear? I've simply taken the same 12 volt. I'm using the 12 volt to drive the motor and to drive the bases as well. Okay,
Yes, sir.
and these two are the 100 kilo ohm resistors. Let me see if I can show you the value. And the reason it is 100 kilo ohms is because you don't want a lot of current to go to ground just because of your switching. I mean, you ideally want to just pull them to ground. Yeah, so it's 1.3 times 100. Okay, screen is visible? No.
So there's a reflection on this.
Yeah, but it's 100 kilo. Basically, take my word, it's 100 kilo. Nothing fantastic to see over there. Okay, any questions so far? No?
Sir, will you show us the hardwired RPM control here?
No, sir. We literally need to combine that circuit and this circuit. I won't be doing it. The output of the 555 should go through a power transistor. That much I'm not gonna do. I've told it in previous classes how to do it. Actually, I was in the middle of making a small PCB for this, but I could not find time. So that PCB will have all the bells and whistles, but it will be based on this. Whatever we studied, it will be literally based on this. I have to put some heat sinks and all, so it may take a bit of time.
Sir, I wanted to ask. So you said that we should never do anything where one single line gets totally connected.
Hmm.
So, but what if we make the connection such that the top two transistors are connected and the bottom two are not? So, would that also cause it to blow up?
No, that will cause nothing to happen. There will be no lower conductive path, so you will have no conduction.
Okay.
Both the terminals of the motor will be at high at some voltage, so there will be no current passing through the. There is no voltage difference. That's what I'm trying to say. You get my point, right?
Okay, sir. So it's not like we are short. It won't short.
No. It won't short anything. There will be no current essentially. So let me share screen and tell everyone what you're asking. So he's saying if 1 and 3 are conducting, but 2 and 4 are non-conducting. That's what you were asking, right?
Yes, sir.
So then this point of the motor and this point of the motor are both at this V in. And there is no difference in potential between these 2 points. So there will be consequently no current flow. I mean, but you cannot do it like that simultaneously using this circuit. I mean, using these cases, you can always conjure up such a case, but when you have made a circuit like this, you have tied down 3 and 4, you have tied down 1 and 2. It is impossible for you to come up with that kind of a situation. Do you understand? I don't know who asked
Yes,
it.
sir.
Manisha.
Yes.
Yeah. Okay. So
Sir, so
let's.
using this circuit,
Yeah. Tell. Using a.
so using this circuit, we can control the speed of the motor and the direction. That's what the
Yes.
use is.
Yes.
No?
Yes. 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 That is precisely the use. And so all this, there are some drivers. So let me share my screen. Wait, one moment. So you can do that, or if you're using uh, not such a high voltage, if you do not require such a high current for your motor, you can use what is known as a full bridge driver. So, but the total current is only 4 ampere. Okay, and it does that 4 thing. I mean, it's a dual bridge. So you see, you have those two logic converters. I mean, sets of logic converters. You have the edge bridge going on. Do you see it? This is the edge bridge. I mean, okay, maybe by just looking at this, you will not be able to. Are you able to see the screen first of all?
Yes, sir. There are two edge
Yes,
bridge.
sir.
Yeah, there
Yes.
are. It's a dual edge bridge controller. It's a dual full bridge. It's also known as a full bridge driver, and it requires TTL logics, and it can drive inductive loads such as relays, solenoid, DC, stepping motors. It can do a lot of things. So yeah, you can use this kind of an IC as well, and your home task will be to just look up how this IC is used, how the connections are. You should be able to at least know how to get your job done with this. So commercially they give you on a PCB, but we now know how to do the full thing, the whole shebang. You don't need to really rely on someone's IC. This is giving you 4 amperes, but the one we made already it gives you more than 10 amperes. So TIP 122 max current. Let's see. Okay, it gives you 5 amperes, but TIP 122 is old. So Darlington, an ampere. Let's see, 142. It gives so 10 amperes you can drive. Okay, this you can use TIP 142 and TIP 142. So the complementary would be TIP what 127. So let's just, so they are known as power Darlington transistors, and you can give a voltage up to 100 volts and 10 amperes, and these are very cheap. They are very cheap. Let's go to shopping and see what kind of asking price is it. So TIP 122 44 rupees. You go to any local shop, you get it for even low price. TIP 147 online they're selling it for 75, but in reality it is very low as well. It should not cost you more than 50 rupees. Okay, so over here TIP 122 and 147, because STI also knows, look, you're looking at some power transistors, so most likely you would need NPN and PNP. So in one go they have given us both the data sheets. So let's see what the ratings say. So maximum voltage you can apply is 100 volts, so you can drive a DC motor which is rated for 100 volts. No problem. Maximum collector current is 10 ampere. Very good. Okay. Is that fine?
Yes, sir.
Let us look at the base currents. So the gain is 500. The DC gain, that HFE, is 500, and they have given some sample circuits how you can switch circuits. So this is exactly what I had shown, if you recall. Yeah. So holding it down to this, or I mean, you can look them up. Now you are in a position to understand those schematics as well. What is the base current? They have not given, is it? Base current is half an ampere. Okay, so here's the difference. I mean, for BJTs, the base current is not negligible. So half an ampere is always going through the base. So you have that extra dissipation. But for switching MOSFETs, so transistors, as you know, or as you will learn, or as you are in the process of learning in electronics, so transistors are current control devices. On the contrary, MOSFETs are voltage control devices. So the dissipation that happens in MOSFETs is significantly lower. That is why if you ever want to build a edge bridge driver, you rather go with a pair of MOSFETs, a P channel and an N channel MOSFET, rather than going with BJTs. But in this course, I have discussed BJTs because it is easier for me to explain without having to explain from scratch what a MOSFET is. Okay, otherwise we would have to spend a lot of time to understand what a MOSFET is. Okay, gate, source, drain, all these things I have to, because hopefully you will be taught this after your midsems in the electronics course as such. So whenever you do that, you will realize how you can easily adapt this circuit for MOSFETs. All right, guys.
Yes, sir.
So let's take a short break. When we come back, we will see how we can drive stepper motors and some applications of commercially available 180-degree servo motors, and we will hopefully be able to conjure up some really good problems for you to ponder about in the assignments. Okay, so don't go anywhere, I'll be back. Hello.
Yes, sir, you're audible.
All right. So we are back, and so now we're going to look at how we can drive stepper motors. So let me create a new file. Okay, we have a new file, and let me just paste over here. Just a moment. So let me just share my entire screen so that I don't need to jump around. Okay. So let me know if it is visible.
Yes, sir.
Yes, sir.
So a stepper motor has, there are various kinds of stepper motors, and the most common one that you will find in the market is what is known as a hybrid stepper. So this kind of thing is known as a hybrid stepper motor. So let me show you the other kinds as well. I get rid of this somehow. Maybe it will go away. Doesn't. So there are stepper motors which look like this as well. So they are unipole stepper motors. Okay, like this. And you can actually drive them with the help of a ULN. There are many drivers available. So we will just discuss in the end some of the drivers that you can use to drive stepper motors. So stepper motors are useful when you need to have precise movement, precise rotations, and otherwise also it provides you a good torque stability at low RPM. So it will not stall unless you give very low current to the driver, to the motor rather. So the easiest way to drive such a motor which has 4 coils, so let me just draw how the 4 coils look like. And one of the coil will be like this, and one of the coil will be like this. Okay, and this is the rotor. So this comprises the 4 coils, 1, 2, 3, 4. And this red and red, they're connected to a single coil, and the black and black are connected to a single coil. So what you can do is you can drive it without a driver as well, and you can exploit the fact that an Arduino can source some current. It is not a lot of current. It is maybe, I don't know how much can an Arduino source, like 70 milliamperes current sourced by Arduino. Let us see what the max current is. I think it can source some 70 or 80 milliamperes. It's not obvious, but it can do it. Okay, so what you do is you need to have a very specific sequence in which current is going in and out of these 4 connections. Okay, to rotate it, you have to first set A1 to high. Just go with it for now. Then everything is low. So this is step 1. Step 2, A1 and A2 become low, B1 is high. Then step 3 is B1 becomes low, A1 is low, A2 becomes high. and lastly B2 becomes high, and then you keep on repeating it. So these 4 steps, okay, these 4 steps. So let me just draw it over here. So let me draw. So let me draw this. So A1 is high, everything else is low. Then B1 becomes high, everything else is low. Okay, this is A1, B1. Then A2 becomes high, everything else is low. And lastly, B2 becomes high. So these 4 pulses, when a stepper motor receives, then it would have rotated by 1 step. Okay, 1 step. And these hybrid motors, they typically have 200 steps in a complete rotation. There are 200 steps in one full rotation. So when this sequence is repeated 200 times, this spindle would have rotated one full cycle. Okay, otherwise it just makes
A1, B1
hmm?
so this A1, B1 are those wires.
Yeah, so if I call them as A1, A2, B1, B2, it is something like this. Okay, so the entire engineering of this is rather complicated, and it is a full-fledged course for electrical engineering. But in this particular course, we just need to see how we can get this to work. So let me just show you how a hybrid stepper motor it looks like. So it is rather complicated. It has a permanent magnet rotor. It has windings. It has a stator, and it has, I mean, 2 sets of teeth. In the rotor cup south, there is a set of teeth. In the rotor cup north, there is a set of teeth, but the number of teeth in them are not the same. They are the same, but they are shifted by an angle, and the number of teeth in the stator. So there are teeth on the stator as well. The number of teeth on the stator and on the rotor are not the same. Usually, the stator has one less tooth than the rotor, and these are all, they are all in the classification of electrical machines, and this is not the course where we will look into the whole details of it. Okay, so with that basic thing out of the way, I mean, how does it look? It has a permanent magnet rotor. I don't want to break open a motor. I don't have a broken stepper motor with me. Okay, there are, so you need to have that sequence of switching. That is, this, the 2 phases should be out of phase by 90 degree. That is essentially what is going on. This is what is that 90-degree shift in the 2 coils. When this is energized, then in 90-degree shift, B1 is energized, then A2, then B2. So 90-degree shift in one cycle. This is not like 90-degree rotation. So this is
Sir,
one single step. Yeah.
sir, are these kind of motors present in the drilling machine also?
No, 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 no. In drilling machine, you have what is known as a universal motor. Okay. In drill machines, you have what is known as a universal motor, and it's a universal motor because it can run off both DC and AC. Okay, so it has, so in DC motors we have a rotor which has a coil, so there are coils on the motor, whereas in permanent magnet DC motors you have fixed magnets like this. But in universal motor, the ones that you have in drill machines and all, this permanent magnet is also an electromagnet. Okay, and because of this you can actually drive it with AC or DC. So the excitation coil and the rotor coil, they are both uh, electromagnets. I can, towards the end of the class, I can possibly bring it to my lab and show you I have made a certain setup and you can see the action, no problem. Or I'll go to the workshop and show. But that is besides the point. So we are now focused on driving a stepper motor. So you need a circuit which can do this kind of stepping, and there are some popular ICs which can get the job done. So the most popular IC is the A4988. Let me show it to you. So A4988 is classified as a stepper motor driver, and let us look at its pinout. Okay, so what do we see? Let's just, so it looks, it's very small, it cannot deliver a huge amount of current. So at best you can drive NEMA 17 motors. So NEMA 17 is like a category of what do you say, motor flange fittings. Okay, it's, the NEMA 17 is typically a small stepper motor, and what does it do? It energizes the four coils in a circular pattern like this. Okay, that is why you have these four turns, and that on-off sequence should be clear in this diagram. Okay, do you see the on-off sequence?
Yes, sir.
So this same
So,
on-off sequence we drew over there as well. Yeah.
so but I didn't get like why there is need of only four. Can I not take much more than that?
You can. The engineering of that stator part will become complicated. In fact, the one I have with me is a 6-wire. So the one I have with me, which I have from scrap, I got it from a scrap yard that has 6. It works. I will show it. I will draw the diagram as well. But this is the
And
most
so,
common. You will encounter this the most.
so
So,
when
but
we
in
are
the diagram,
putting one as a high and others are low, then it is rotating. Then can I not do like only keeping one as a high and it will be rotating?
No, it will not rotate. So this electromagnet, when say when this is high, it will attract the permanent magnet rotor one step towards it. Now it will just stay in position because it's like north south has attracted and it's not gonna move anymore. Okay, I mean loosely speaking, it is something like this. So this is the coil. So suppose this becomes north, and this is the permanent magnet. Suppose so south north. So when this is energized, this south will go towards here, and this thing will lock. You need to go it further. You need to make it
Okay,
go
sir.
further, right?
Yes, I got it.
So then this has to become north. But here's why those two stator cups are required. Here's why those two stator cups are required. When this so this is how the stator cup is shifted. Like I said, the south and the north cups, they are shifted slightly. It is something like this. So when this is energized, the rotor, this is fixed. These two are fixed. Imagine. Is everyone following? You have four coils. Okay, and suppose initially nothing is on. Suppose initially nothing is on, and you are something like this. Okay, so when this becomes on, this becomes north, everything else is off. So then, I mean, I'm just giving you a working idea. This is not exactly how it works. So this will be attracted. Okay, come on. This will be attracted. Okay, like this. Okay, now you turn this off, turn this on, north. Now what will happen?
The south will be attracted towards.
The south will be like this. So this is the next step. Now you turn this off. Now you need to rotate this, so you have to make this south. So that is why that coil sequence is important. So now when you make it south, this will repel, right? No, sorry. This has to become north only. This has to become north only. So then what will happen? It will rotate like this. Then so on. Then this north goes here. Then this
Sir,
thing will
sir, I
rotate
have a
like,
question.
yeah.
So, like when we are stopping this motor, so suppose a case occurs that the magnet aligns with the coil, and then then we are applying the magnetic field again when we are starting the motor, so then it won't rotate.
It will rotate because of the fact that the two rotor cups are offset. Okay, that is why that offset has to be there. Otherwise, it will just stay in place. It will never rotate again. Let me
So
see
like
if I can. Yeah, ask.
so the timings for which each coil gets excited, is it like calibrated so that it matches the time it would take the coil, it would take the magnet to rotate?
It happens very quickly, but if you try to get it too too high of a speed, then it will not work. You will start what is known as missing steps. Okay, you will eventually start missing steps. Okay, so here in
So so
this, yeah, tell.
so doesn't the inertia of the magnet make it keep
No, the
rotating?
number of steps are so small that this machinery doesn't rely on inertia at all. Okay, it doesn't rely on inertia. I think it has 50 teeth or something, the hybrid ones. Okay, and the
Okay.
offset is just minuscule because it has 50 teeth. See, this is the north cup, this is south cup, and it's just offset so ever so slightly. Okay, you understand what I mean? It is offset ever so
Yes.
slightly, and that causes the entire thing to rotate. See, I mean, it it will take us a lot of time to discuss this in its full glory. Okay, this much I can assure you. So we will not cover this, unfortunately. It will take us a lot of time if we want to consider the engineering of this. So the north and the south, the gap between the tooth that you see over here, the red one is the front cup, the blue one is the back cup, and so that small gap is offset. The back rotor is offset by that much. It's a very small degree. Okay, it's a very small degree, and even the rotor, the stator poles, the number of teeth that it has, it's very carefully done. The coil is done in such a way that the opposite poles are north south always. So it requires a lot of engineering. It requires us to really take a step back, first understand how DC motor works. So essentially it is sort of a very high end DC motor if you want to look at it that way, but it does not rely on inertia, and there is no requirement of commutator rings. Okay, there is no requirement of a commutator ring. I think you can see the offset clearly in this diagram. I think the offset is very easily visible in this diagram. These
Yes.
teeth, they are not aligned. Okay, the teeth are not aligned. Okay,
That you initially you draw two coils. What was that then?
which coils? These two.
These-
They are the
Okay.
stator coils. This stator coils. I have drawn two, but there are actually multiple. But two is the bare minimum you need. Two logical coils. So don't think that these are all individual coils. So you coil this first, then skip this stator block, then you coil this next, then you skip this stator block, then you coil this next, skip this stator block, coil this, then finally you have only two terminals coming out. Then for the other two terminals, whatever you had left, the stator blocks, you coil it, go to the next block, coil it, go to the next block, coil it, go to the next block, and so on. Okay? So that's what I mean. DC motors also have this, unless and otherwise you know exactly how a DC motor works, it will be very difficult for you to understand how stepper motor works as well. But for now, don't worry about it. You can learn it separately. You can come down to the lab, you can break it open. Not mine per se, but if you have a stepper motor, you can break it open. You can see how it works. So how many does it have? 1, 2, 3, 4, 5, 6, 7, 8. Okay. And the teeth, they are, if you look very closely, they are closely meeting with the stator, but they will never align. Let me just copy this. They will never align. If they align, then you will never have any rotation. There is a small offset between the stator and the rotor. I've told this many times, but this you will be able to see extremely clearly over here. See, align, slowly they are going apart. Now misalign, 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 misalign. Misalign, 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 misalign. You see? Align, 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 misalign, misalign, misalign. So this misalignment is important for the operation as well. And this you are seeing the north cup of the rotor. The south cup is in the plane, so the teeth of the south cup will be occupying these places, but they are in the back side of the rotor. Am I able to convey what I want to say? These are the places where the teeth of the south cup will lie, and they are offset with the north cup by exactly this tooth angle. Is it clear?
Yes, sir.
At least roughly speaking, how the construction looks like. So it is a complicated electrical machine. Don't have to sweat it. Don't have to really bother so much about it. Just need to know that the sequence of the coils has to be like this. It has to create a rotating magnetic field. That's what I want to say. This creates a rotating magnetic field. Okay? This creates a rotating magnetic field. It doesn't rely on induction, so it is not what goes on in a single phase induction motor. In a single phase induction motor, there are no permanent magnets. And by not having any permanent magnets, single phase induction motor always runs at synchronous speeds. This you might have studied in your first year. Yes?
No, sir, induction motor was like, because we couldn't complete that part.
Yes, sir.
Okay. So given that information, it will be then even more difficult for you to grasp all this. But never worry, we are not here to study electrical machines. We are here to understand how we can make things work, how we can make a stepper motor driver. Not make it from scratch, but how we can use such easily available drivers to drive stepper motors. So the point is, you can see that when the sequence is correct, you will have a rotating magnetic field which causes the internal permanent magnet rotor to rotate. This is all you need to know for the moment. Okay, this is all you need to know at the moment. And let us look at the chip outs, the pin outs. So you have enable 1, MS1, MS2, MS3. So MS1, MS2 and MS3 are what is known as micro stepping switches. MS1, MS2 and MS3 are what are known as micro stepping switches. We will discuss this later on if required. There is a reset pin, there is a sleep pin, there is a step pin, there is a direction pin. Apart from this, there is a voltage input pin, there is a ground pin. This is for powering the motor. These two pins are connected to the motor coils. 2A, 2A, 2B, 1A, 1B are what are known as the coil pins. So these four pins connect to the motor coils. The IC, that is the A4988 IC, it will decide the sequence appropriately how to have this kind of a switching between these four pins. And during switching, it will apply a V mode and ground across those pins. And lastly, you have VDD and ground. So VDD and ground is the power required for this circuit board to be powered. It does not draw power from V mode and ground. So V mode can be different, VDD can be different. Okay. So Typically a NEMA 7, I mean any my hybrid stepper motor has 200 steps per revolution in what is known as a quarter step mode. Okay, but if you have no, sorry, in full step mode, I don't know why I read that. So when the 3 pins are low, so the 3 pins expect a high or low input, meaning something like an Arduino, if you give ground to the 3 pins or no connection to the 3 pins, it will remain low. If you give high to one of the pins, low to two of the pins, it will go into half stepping. So half stepping is possible, or partial stepping is possible only in hybrid stepper motors, where using one half step, instead of 200 turns per revolution, instead of 200 steps for one complete rotation, you will now require 400 steps for one complete rotation. If you make low, high, low, then you will have a factor of half again, then similarly another factor of half, and then another factor of half. But it is not desirable to do so because it compromises the torque. So it is always desirable to run them at full step, meaning 200 steps per rotation, and that is good enough for many applications. The control inputs of the A4988, so the driver chips that drive stepper motors have two pins. One is the step pin and one is the direction pin, which act as control input pins. So when the step pin is high, it will step, it will create one entire sequence of this. When you put the step pin to high, it will cause this 4 sets of switching on and off to happen. When the direction pin is high, then there is one notion of rotation of the motor. When the direction pin is low, it will simply reverse the direction of the motor. Now what do you expect when we say that when you give one step pulse to the step pin, it will execute this? So when I have 200 pulses, going to the step pin, the motor shaft will complete one rotation. So the step input can be given theoretically with what circuit that we have made so far?
Sir, IC 555 is stable mode.
So we can use the 555 in stable mode to give these step inputs, or you can use a pulse width modulation from the Arduino or any other microcontroller that you like, but basically this requires a pulse. One pulse corresponds to this entire sequence. But now if the pulses are too fast, then what will happen? The time required for that stator to attract the rotor, that much time you have to give the motor. If the steps are too fast, then again you will start missing steps. The stepper motor will start to miss steps. Okay, so the step should not be too fast. You can have it slow, no problem. But when the steps are too slow, suppose the steps are coming in very slowly, what will you perceive? You will perceive that the shaft of the stepper motor is rotating, stopping, rotating, stopping, rotating, stopping, and so on. There will be no missing steps, but it will do that. Okay? And that's it. Forget about the enable, reset, and sleep. We don't need to know that. These are the 4 winding pins. And of course, because it draws 1 ampere per coil, which is quite minuscule, and it can supply a maximum of 2 amperes per coil. And actually you can set the maximum amperage of this chip with the help of this trim potentiometer that is given on board. So you have to apply the a voltmeter between the ground and one of these pins, and when you rotate this, you will be able to see how much the maximum current is. We don't want to discuss this right now, but yeah, typically if you want to drive the stepper motors at 2 amperes, you need to give a heat sink, otherwise the chip may burn out. Okay, so this is the current limiting potentiometer that I just spoke about, and I will share this link as well. You can have a look at how you can use a voltmeter to actually determine how many what is the maximum amperes that this IC is currently set at. Okay, but it's not super difficult to understand any of this, to be very honest. Okay, so similar to this A4988, there is yet another very popular driver, and that is called as the DRV8825 driver. So this is also a stepper motor driver. It's known as the DRV8825 driver, and even that has a similar way of operation. It has a very similar pin out as well. Enable micro stepping pins, reset sleep step direction, power voltage input to the motor, ground of the motor, coil pins B1, B2, A1, A2. Whether there is a fault, it is, I think 10 is an out pin, but not required for us at the moment. And 9 is the ground logic. So the Arduino ground, if you're using an Arduino to drive everything, it will go in pin 9. If you use a 555 timer in an astable configuration, the ground of the 555 must be connected to this ground logic because it is the logical ground. This step again receives PWM signals from either a 555 astable oscillator or some kind of PWM generator, which could be through your favorite microcontroller like a Raspberry Pi, an Arduino, or anything that you like. Everything else is the same. The mode of operation is the same. Okay, you can use this as well, no problem. It is also provided with a heatsink, and it can supply 1.5 ampere without getting overheated. Okay, it can supply a maximum of 1.5 ampere. It also has a small trim pot over here, which with which you can control the maximum current which the coils will be receiving. If you intend to use the chip for driving stepper motors which demand more than 2 amperes, then you must stick on top of this a heatsink. Otherwise, the IC will burn out. You will get some magic smoke. Well, these are the ICs with which you can drive small stepper motors. This is the bigger version of that, and it is used to drive larger stepper motors. And the one that I'm going to show you today is with the help of this. And the TB660 stepper motor has an output current of half ampere to 4 ampere, so it's quite beefy. The control signals are also not low voltage tolerant, they can go to higher volts. The maximum power that you can drive through this is 160 watt. It also has full step, quarter step, half step, quarter step, 1/8 step, 1/16 step, and 1/32 step. Okay, so let us look at the wiring diagram for such a motor driver. For such a motor driver, you must connect the power source for the motor that can take a voltage from 9 volts all the way to 42 volts. So you have VCC and ground. Then you have A plus, A minus, B plus, B minus. So these are the 4 coils of the stepper motor, and you can see how they are connected. So this is one coil which is B plus, B minus. This is the other coil which is A plus, A minus. Apart from this, you have then the control pins. So you have enable minus, enable plus. Then you have the direction pin, you have the direction plus pin, you have the pulse pin, and you have the pulse positive pin. All the pulse positive, direction positive, enable positive pins are to be connected to 5 volts so that you have all the functions enabled. Hello? Someone wanted to ask? Okay, that was probably for someone else. So all the plus pins you have to connect to logical high. In this case, it is 5 volts of the Arduino or any other microcontroller of your choice. And all the negative pins are connected to some kind of input. So enable minus, when it is given a ground voltage, then the entire motor will turn off. Enable minus, when it is given 5 volts, it will turn on. Direction minus, when it is given 0, it will rotate in one direction. When it is given a logical high, that is 5 volts, then the direction of the motor spindle will reverse. pulse pin is again fed by this green wire which is connected to pin 7, and through that you have to give a pulse width modulation. Okay, so you have to declare them as output pins. This is quite obvious, you might have done it in your DIY lab. Okay, so pulse, so what is going on? See, pulse high, then 50 microseconds it stops, then pulse low, then 50 microseconds it stops. Okay, so this is the main high low that this pulse is waiting to take. So you can do it in code using this, or you can simply plug it to a PWM generator also. That is not a big deal. Is it clear?
The direction pin changes the direction of the motor.
Yes. So over here it's forward, so direction is kept low. When you want to reverse the direction, direction is kept high.
Okay, sir.
There's some people in the background discussing something. Has anyone else heard it? वो करते हैं, load करते हैं, something like that. Anyway. Okay, so this is the big beefy driver. Whenever you use bigger motors, you use this, and the heat, the back plate of this driver is made from aluminum. So the IC is pasted on with the help of thermal paste to the aluminum heatsink. You don't need to worry about cooling it in any other way. Okay, so let me turn on the camera. Let us go down and let us see how this thing can be done. Before that, I'll just tell you what kind of motor I have so that you don't get confused. You have such kinds of motors. There is a center tap in the coil as well, so you have 6 wires coming out, 1 2 3 4 5 6, and this is the rotor. It's nothing fantastic. You can pass the oh, come on. You can pass the coils, you can pass the driver output to 1 and 2, or 1 and 3, or 2 and 3, no problem. You can pass the output to 4 and 5, or 4 and 6, or 5 and 6, no problem. Okay, it's just a center tap coil. So whenever you see 6 wires, you should not get confused, and I will show you how you can figure out which coils are which. Okay, so far you've understood that rotating magnetic field is to be created, and that is done with the help of an IC. There are various kinds of IC. There's a A4988, there's a DRV 8825, there's a TB6600. There are many such ICs which are present. So let us see. Let me just go down and you can see that in action. Okay. So yeah, I made a small testing unit. So I put an Arduino, I put a small screen. I did all this so that the wires are not flailing around all the time. So finally the output of this small box are 4 wires, and this is basically using a TB6600 stepper driver. It's using a TB6600 stepper driver. Okay, so I have a flip switch for enable for direction reversal, and I have a knob for the speed control. So this is the uh, stepper motor. It has 6 wires. As you can see, it has 6 wires. Can you see it? Okay. Can you see
Yes.
it now? So how do you figure out which wire is which? You just take a multimeter, and as you can imagine, if you just go into continuity or resistance mode for the last part, you should be able to figure out whether the coils are shorted. So let's take the blue and the white. So they are shorted. So we know that blue and white are parts of the same coil. So let's take yellow and blue. So there is no connection. Yellow and white also, there is no connection. Now orange and white, there's connection. So orange and blue also, we should have a connection. Okay. Similarly, red and black, let's check this connection. But red and white, red and blue, there should be no connection. Okay. So we've just identified the two coils. So blue and white, they form one coil, and it shows 6. I mean, at such low values of resistance, really you shouldn't use such kinds of meters, but that's fine. So it shows something in the 6.5 ohm regime. So the coil resistance is 6.5. Okay, so what I'll do is I figured out what the 4 coils are. I'll just take my driver circuit and I'll screw them in. So
So
could have
those wires
used,
we short them
huh?
are part of same coil.
What?
Wires, those wires we got cut,
Ah,
they are part of same coil.
I'm sorry, I could not get you.
So the wires that get short circuited and we use circuit, they are part of same coil. And they will be different.
I don't know whether it's my connection problem, but barely able to understand you. Can you write it in the chat? Have you written it in the chat? No. Others. We are getting short circuit. Yeah, they are the part of the same coil. You're correct. In the other coil, that is why you don't get any continuity, because they are something different completely. They are not connected. So I'm just making 2 of the wires no connection, doesn't matter, because I have a driver for 4 wires only. So let me plug this in. Okay, so you have this rotation. Can you see it?
Yes.
Yes.
Now I can reduce the RPM. Okay, low RPM. I don't think you can see it all that well.
So yes, so we can identify that.
Now it's even lower RPM. Okay. Fine.
Yes, sir.
Now you can reverse the direction as well. So let me make it high RPM. You see? Okay. So what are the uses of them? I mean, stepper motors can be used to drive various mechanisms. So you've learned various kinds of mechanisms, right? Geneva wheel and all this. Quick return mechanism.
No, sir.
Oh,
No, sir.
okay, okay. I thought you had learned it, but anyway, let me show you a quick return mechanism. So this thing over here is a quick return mechanism that I had built for teaching people a quick return mechanism. So it's rather helpful. So let me just strip off the wires real quick. One moment. So first things first, we must identify the four coils, and typically it is black and green, but we don't want to take the risk. We'll do it the hard way, no problem. I mean, it is worth spending time to do this, otherwise, your thing might not work. So it is black and yeah, black and green and red and blue. They are the okay. You could not see it. Maybe it is slightly off camera. I mean, you take my word. Black and green, blue and red. They are the coils. So now we'll make the connections. Would have really used some spring terminals, but that's okay. So basically, you can think of any application where you require precise stepping, those 3D printers and all that you saw, right, the other day. So all of them, they make use of such kinds of stepper motors because you can precisely have a certain amount of rotations without having to worry about whether there is encoding or not. So the encoding is not there on a 3D printer. It's only once the home position is known and the gear ratio of the tooth belt is known, then you can simply drive. Okay, this is Do you understand? So you don't need any encoding. The encoding is all natural. One step. So 200 steps per revolution. So if you have one step of the stepper motor, one pulse, how many degrees will it go?
1.82.
correct
1.8.
correct so that is precisely, and that's a very small angle if you think about it. That is not a big angle, so you really have a good precision already going on. So in 3D printers, in CNC machines, such kinds of stepper motors are used, and stepper motors are also, you can connect what is known as a encoder to the back of the stepper motor, so that if you feel like your application requires a very high amount of torque, right, if you feel that your application will require a huge amount of torque, so there is always that doubt in the back of your head that maybe there will be steps which are missed and so on. So if that doubt is there, you can always use a shaft encoder which is sold as a servo stepper motor. So that servo mechanism tries to always compensate for it. If it misses a step, it will try to provide more current to the coil so that it can do that step. Okay, so the four wires are connected eventually. So let's see. Okay, so what do you see?
So due to rotation, we are able to get the linear motion, linear in simple harmonic motion type.
Yeah, that's fine. You can see a few steps being missed. I'm not sure whether it is visible on camera.
So like some stoppings are there, no?
So now the motor has stalled. Okay. It was drawing current, but it stalled for some. I mean, it's become rusty, so the contacts are rusty. I need to. I mean, it's lying around in the open for a while. So let me just replug it. It should be fine. Okay, so you can connect a hacksaw over here. You can have automatic cutting of something. Can you imagine? I mean, you can use it for many applications. So it's a. Is it a quick return mechanism? No, this is not a quick return mechanism. Small home task for you to figure out what this mechanism is as well. What is the name of this mechanism? Okay. Small home task for you guys. Okay, so this is how you drive stepper motors. Any doubt?
Sir, you're on mute. You're not audible.
Okay, so we have come to that point where someone put me on mute. That's okay. But anyway, this is how stepper motors work, and so your home task will be. I mean, I'll define it completely in the document.
Sir, excuse me.
Yeah.
Sir, can this replace the working action of a cam?
Yeah, you can. In there are camless engines. Something like this only happens. I mean, camless engine meaning it's not connected to the camshaft. That's what I'm trying to say. There is no timing belt, nothing. It's direct firing. Let me see if I can quickly show you how. What is the time? We have 10 more minutes. So let me first show you some applications of a for DCs of a servo motor, one of those 9G servos, and then we will see how those uh, alternating no, universal motors work. Okay, we'll just wrap it up with that today, so just give me a moment. Okay, so you can have such a variety of motion with the help of servo motors, which only restrict motion to 120, 180 degrees. So they are half ton servos. So right now you can see that the servo is carrying a small test tube around. I mean, it's pre-programmed. I've pre-programmed it. So this was, so the whole mechanism was built way back by Rishabh Singh, who is your senior, and some of the parts of the programming is done by Shreya Verma, who is also a fifth year student now. So I mean, nothing super complicated, but yeah, someone has to do it. Okay, so you can figure out that using various mechanisms and how you can actuate those mechanisms, you can achieve a great degree of flexibility in motion. You can achieve automation in doing various tasks. So this will be part of your reading assignment. Are you able to see it?
Yes, sir.
Yes, sir.
It's pre-programmed to do it in a loop. Okay. Give me a thumbs up if you like this. I mean, I don't know how you can give a thumbs up to this. Yeah, like that. Perfect. So it's all about having mechanical actuation with the help of electronics. The whole part is 3D printed. You can figure that out. So you can do such things nowadays at the comfort of your home as well. Okay, so let me go to the workshop and show you and those PMDCs and uh, universal motor. So just give me a moment. Yeah, okay, so we're in the workshop. And so, yeah, this is how that small setup looks like. So, okay, this is better, right? For the, I don't know. You're able to see the rotor?
Yes.
Yes, sir.
This is the rotor. And right now, if you look at, if you look at this, this part and this part, they are the carbon brushes. This part and this part, they are the carbon brushes. And they are electrically connected to the commutator ring. Okay, so first we will use a permanent magnet. So right now, this is the permanent magnet. There's a magnetic, I mean, ferrite magnet stuck over here, and let us give it power. Okay. So this is how those permanent magnet motors work. So I'm switching it off. So I have over here a power switch. I have over here a toggle switch for DC AC. Right now it's on DC. Okay. So this is important because when we will use an electromagnet instead of the permanent magnet, we will see that it works both on DC and on AC. So I'm going to switch off the power. Now I'm going to swap the permanent magnet with the electromagnet. Yeah, hello. Am I audible? Yeah.
Yes.
Yes, sir.
Yes, sir, you are.
So this is the exciting coil, which is basically the electromagnet, which is replacing the permanent magnet. So let us switch it on. So it works. So right now it's on DC, so it appears to work. Okay, but the thing is, we can put it on AC, and it still works. So right now it's on AC, and it still works. Right now it's on DC, it works. So using the exciter coil, we can make it work using both DC and AC. Okay.
So in the permanent magnet case, it will not work on DC AC.
What?
In the permanent magnet case, it will not work on AC.
AC will not work. Okay. Okay then. So that's all I have to discuss this week. So next week we'll try to cover operational amplifiers. Hello.
Yes, sir, we heard.
Hmm.
So we can hear.
Yeah, yeah. So next time we will cover operational amplifiers. So that's all from me today, and I wish you a good day remaining. It's a long week, so do go through the study materials.
Excuse me, sir. Sir, can you tell which software are you uploading the files from?
Pardon me.
The files that you write in which software are you uploading those from?
External plus plus.
Okay, sir.
Yeah.
Excuse me, sir.
Yeah.
Sir, I had a doubt in the week 2 assignment tasks. Sir, can you give a hint for that linear encoder thing? Means linear position encoder, how to manage that?
Okay, you send me an email. It is difficult to explain just by saying. I can perhaps draw you some schematics and send.
Okay, sir. And sir, for the rotation direction means sensor means what is the ratio between that gap and that teeth? Because that will be the key thing, I guess.
Yeah, yeah, that will be the key. So you assume a certain gap. You just
So
put
means
down the logic
I
and the
can just
circuit.
I can assume from my own the
Yeah,
ratios,
yeah, yeah.
like.
Of course, of course. In the absence of any hardware, you can do it. No problem.
Okay.
Okay. All right. So I'm gonna stop recording and we can